So happy to see you all here. We're going to talk a little bit about the views that we have defined on top of table loggers. You already had like a DevRel session like this one with Devon, where he presented the table loggers. One thing that you did not see then is that the table loggers, the name log we know, right? Is like essentially, it's not a log file. It's the actual tables that we can look at in the UI, and they are defined inside the server. They are called loggers just because they log data, one line after one row after the other. We have a couple of views defined on top of them with actual, if you look at the definition of these views in the code, is in the performance queries, the Java file. You can look for it in GitHub and take a peek at the file if you want. These are actually views like something that you could define yourself in the UI, right? It's just a table expression with column expressions that it does filtering, it does update view, and the intent really is to make some of the data a little bit more user friendly for a first look. Okay, the idea is that the table loggers themselves have data that is raw data, right? It's just what we collect. So we have as much precision as we can have. So for instance, we have time units in nanoseconds, right? How much CPU are we using? Well, we took this many nanoseconds. Nanoseconds are not super friendly to look at and not very intuitive from a human perspective when you're trying to make sense of something quickly. So maybe it's a better thing to show you in seconds with a fractional part, which is, by the way, if you're like used to work in Python, is what typically you do see in Python for time units, right? So anyway, the table loggers are there with the raw data in case you want to build your own, and over time you probably would want to, right? And if you're doing some kind of like drill down and really want to understand what's going on. But in terms of some kind of like, basic monitoring of how the system is doing, these views defined in the performance queries, the Java file, give you the moral equivalent of the high-level tools that you have in Unix, like top, right? If you feel that your machine is slow, the first thing that you reach out for in the Unix world, in Linux, is you run top and you try to see what's going on, what's running there. These views essentially try to fill that role, okay? So I'm going to show you one of them in detail. It's a fairly recent one. We just modified it this week and it was merged yesterday. That shows the state of the server in terms of memory utilization and CPU utilization from the point of view of what it matters to us, which is the update graph processor, right? We have by now an understanding of what the update graph processor is. We essentially disseminate updates to tables that are ticking, right? And we do that in a schedule, right? We essentially configure the server. There is a default. Every second, we essentially disseminate updates. That's the configuration, the default configuration for community. You can change that. There has been some talk that maybe it will be better if we define this to be 100 milliseconds, 10 times a second. But right now, the default is once per second, okay? And the thing is, as you do more and more with the service, if you have more tables defined, if you're subscribing to more Kafka feeds, if there's more going on, of course, there's more work that is going to happen there. And at some point, you may be running into issues where, well, actually, I'm not able to do all these in the period that you have defined for me in 1 second. Maybe I'm taking more and more, right? And that's the kind of thing that we're going to try to look at in this one table that I'm going to show you. So I'm going to present now. So you're looking at a command line in just one of my clones, okay? I'm going to go to Deephaven perf. I'm going to be running the Docker Compose inside Deephaven perf because in this way, I have an easy way to generate a lot of load, which I need to do in order to be able to show you a server that is under load, okay? But that's the only reason. This gives me a way, an easy way to define a couple of tables and get a lot of Kafka messages coming in so that I can show you a server under stress, a server under load, okay? So I'm going to start the parts of that compose that I really care about. That compose is fairly complicated. So I'm not going to start everything on it. I'm just going to start what I need for Deephaven itself. This compose also has materialize so that we can have a configuration where both materialize and Deephaven run in parallel. We're not doing that today. That's why I'm being explicit here. You normally just say Docker compose app minus D, that minus D is detached, and that's it. It will start everything. But I'm saying explicitly, these are the things that I need. Okay. So with that, I'm going to start the server. The last time I ran out of memory. I have the server now, and this is the definition that I need for this logger that I'm going to show you, this view and a logger that I'm going to show you. And I'm going to show you both the logger itself with the raw data and the view on top of it. In the new Deephaven Python, in the Deephaven 2, as we used to call it, these are in the perfmon package. So I'm importing that. And the raw logger is the _log version. And the view on top of it is the one that doesn't have _log, and this is called server state. This is a table that used to be called process memory because, you know, until last week, it only had memory data. But now it also has information about our update graph processor cycles, which I'm going to talk about in a second, okay? So I have the raw data here, and I have the view here. I'm going to start sending some more interesting amount of messages. This is a script that sends a certain amount of Kafka messages per second so that we generate load. Before I do that, I'm actually going to create the tables for this demo. So I'm just loading a script with the materialized demo implemented on top of Deephaven. This generates a couple of views that depend on some Kafka messages that are going to flow. We have some ticking tables here. And we're ticking very slowly right now from the point of view of incoming data. We just have 50 messages per second. So I'm going to come here and I'm going to change that to 50,000 messages per second. And you know, this script is verbose. It tells me, okay, we're going to set these page views per second to 50,000. It used to be 50. Okay, so now we actually have more data coming in, okay? We define a couple of tables, so I'm going to go back here to the table that we care about, which is server state. So I'm going to give you an overview of this table, okay? So we are every 15 seconds taking a sample of the server state, okay? So this table is going to grow 15 seconds at a time, one row, okay? It's just going to continue appending that way. We take samples every 15 seconds. The 15 seconds is configurable at server start. So you could change that. We found 15 to be a good trade-off between too much data too frequently and having to wait too long for the next update. So the first part of the information, the first column is just which particular timestamp is when this particular 15-second interval started. The second column is how long this took. We cannot be exactly precise for when we cut, so sometimes we have like, you know, plus minus 1 millisecond or so, okay? So that's why we want the actual length of the interval here expressed. After that, we have a couple of columns that have to do with memory utilization, and this you may have seen before because they used to be here when this table was called process memory. We have the used memory in megabytes, MIB, meaning, you know, the power of 2 version, not the base 10 version, okay? So this is like 1 kilobyte, 124, 1 megabyte, 2 to the 20, etc., right? The way this is presented is different, and this is where we should see the beginning of the value of having this as a view with more user-friendly data, right? The raw data that we can capture from the Java virtual machine in terms of what the runtime offers us, right, is the total memory in megabytes and the free memory in megabytes. And this is somewhat complicated in this sense, okay? When we start the JVM, we tell the JVM typically this is the size of the heap that I'm allowing you to use. This is the maximum heap that you can use. We're used to be aware of that value because when we need more memory, we need to increase that, right? we normally, I don't think, are used to think in terms of where do we actually start, because typically we do not take that amount of memory. Let's say if I configure a heap of 30 gigabytes, typically we do not get 30 gigabytes right away when we start, right? Uh, the actual utilization of the JVM as a process, if you were to look at that in top, is going to grow over time, and it's going to be able to reach that point, and then it won't be able to get more because that's a limit that we set for it, but it will not start using that much. So what you get from runtime, when if you were to look at the Java doc for the type of data that you can get in the JVM in terms of use memory, you see the total memory, which is what we have requested from the operating system so far, which is typically under our limit when we start, and of that, how much is free. So the Java process itself has this amount of memory available to it from the operating system, already requested, already part of the process. And of this memory, we can see here, we have around 5 gigabytes requested. This session, by the way, is configured for 12. I have Deephaven configured for 12, sorry. And the amount of free is 1 gigabyte. So we're using 4 out of 5, right? Well, we calculate that for you here. You typically care about how much available memory you have. And the definition of available memory really should be against the maximum limit that you have configured, which we also make available here, right? This number is a little bit silly to be in a table because it's essentially the same number, because that's the limit. The limit is not going to change, but it's useful to think in terms of, like, the actual limit that you can reach. So we have right now available 7.9 out of 12.3. Okay. Okay. So far, so good for that. Even easier, we can look at the ratio, right? So we have 64%, 60% available out of the 12 gigabytes that we have defined. We are using, you can see this ratio decreasing, by the way, because these tables that we have defined in this demo, they are append tables, and as more Kafka messages show up, and we're sending, an interesting amount, we're sending 50,000 per second, the tables actually grow and the memory utilization of the server grows, okay? Okay, cool. So that's about the columns that have to do with the memory. Now let's go to the columns that have to do with the update graph processor statistics, okay? So since we have the configuration for the Deephaven community set for 1 second update cycles, right? You will expect that in one row that is showing 15 seconds of activity, you will get to run 15 cycles. That's happening. So it's like, great, this is the number of cycles that manage to finish in this interval. And a small caveat here for you to keep in mind, we have a 15-second interval, and then we have update cycles of certain length on top of that 15-second interval, right? It's totally possible that in our 15-second interval, at the time the interval started, there was an update cycle already running, right? So there is a question there. Okay, I mean, where do we measure this particular update cycle that did not completely fall into any one of these two sampling segments for the table? Well, we decided to sample at the end. So we are sampling at the finishing point of the interval. So for this particular one, one that overlapped the beginning, the start, we actually counted as part of this cycle. In this case, if didn't manage to finish by the time this interval finished, we will not count. Okay, something interesting happened, which is we are using more and more memory because these tables are growing, and we have a little bit of GC happening. It's actually showing us in a different color when the GC activity, when the amount of GC time over the 15-second interval goes above a 5% threshold. So we're using a more interesting amount of time in GC, and you can see as I scroll through this table, right, we have been using more time on GC because at the beginning, I was not sending 50,000 messages per second, so nothing was really happening, but then more time was happening in GC. I didn't describe for you this column before. So the GC time ratio is essentially of the 15-second interval, how long the JVM was actually doing GC instead of letting us run. Okay, so we actually don't have the 15 seconds available to us to do compute and do everything. We have a certain amount of time that is used by the JVM right now to collect garbage and to essentially give that garbage available to us as free memory uh, after that. Okay, cool. So I'm running pretty low on memory right now. So what I'm going to do is that I'm going to restart um, to actually generate a load in a different way. I mean, actually more load so that we can see uh, the update graph processor starts hit. So I'm going to reduce the number of messages just to be able to describe to you um, the other columns before we run out of memory, because if I didn't do that, we will run out of memory pretty quickly, okay? So to describe the rest of the columns that have to do with the graph processor cycles, this is 15. You see here we have one case of 14, one case of 16. It's not exactly precise 15 because of this problem of what starts and what ends. So it's you cannot expect exactly 15 on every round, okay? This notion of update graph processor on budget is this idea. We are defining 1 second refresh cycle, so we are expected to start refresh every second, okay? If our cycle were to take longer than 1 second, then of course we will not be able to abide by that commitment, right? So we say that a cycle is on budget if it actually managed to finish in 1 second or less. This is showing us that some number of cycles are not finishing below 1 second. And we have some stats here that actually are showing us how the cycles are doing in terms of how long they took. In the raw data, we actually have all of them in a column that has an array. So we have all the values for how long it took for the cycle to finish in microseconds on the 15-second interval. Looking at a table with an array value on it is interesting and valuable from a programming perspective if you are doing like some overall stats coding on top of it. But from the point of view of a human trying to make sense of what's going on, it's hard. So we have some statistics, and we have, for instance, the max cycle here, right? So before, right, when we started, the cycles were not taking very long, okay? At some point, probably when I loaded the script, right, we had a very long cycle because there was a lot of effort done for the initial setup of the tables. So it's not uncommon for if there is a sizable amount of work to be done to define the initial state of a table, and there's a lot of that script unloading the full script, it's not uncommon for have that cycle in the initial definition to take long. So we have a cycle that took 2.7 seconds, way over budget, right? Sorry, right? But then we went back to cycles that maximum were, around 0.6 seconds, 0.4 seconds. So we were doing fine, right? Aside from the max itself, we have the median, the average, the mean, and percentile 90 of how long the cycles take, okay? And then let me look at if there is something interesting. Yeah, this same example is a good one. To be honest, the mean, the average is pretty useless here, okay? It's a stat that everybody expects to have and to see when you show stats of things, but on measurements that have to do with latency and performance in computing, typically the average is not very useful. And this row is, I think, a good way to illustrate what's the case, why that's the case, right? We had one cycle, which is very likely the cycle where we had to define these tables that took very long, 2.75 seconds, right? But you can see here that the median is 0.01 seconds. So every other cycle in this 15-second interval was fine. It was just one cycle that was out of whack, right? Because it was a special circumstance, right? It's very frequent that in latency measurements, you see things like that. So if you look at an average, it's very, very misleading. And you can see here that it's very misleading because this thing pushed the average higher, a lot higher than otherwise it would have been if that one outlier wouldn't have been there, right? So the presence of these outliers in latency measurements typically make the average a pretty useless stat to have. It is in this table because if we don't put it in this table, we're going to get more questions from customers about why it's there. And we're going to be wasting time explaining that. So it's easier just to have it here. Or at least that's my humble opinion. Maybe we should remove it. And the P90 is really percentiles, higher percentile, right? It's a very common thing in computing. I mean, Google SREs define guarantees for Google Cloud in terms of SLAs, service level agreements, and the service level agreements are typically defined in terms of percentiles of 90, 95, or 99. These higher percentiles are a way to essentially say, you know what, take out certain number of outliers, right? So by saying P90, we're already taking this guy, which is one outlier, out. So, okay, cool. These are these columns, right? This UGP update graph processor time ratio is almost the last column that I want to mention to you. And this is a good proxy. It's not exactly, but it's a good proxy to think in terms of CPU utilization, okay? So if this table was the output from top, from the Linux Unix utility top, this will be the CPU utilization of our update graph processor. Why? Because what this ratio is really showing is this, okay? We had 15 seconds available in this particular sample for this row, right? In this 15 seconds, we had 13 cycles finishing. Those 13 cycles in total use a certain amount of time. If that amount of time we divide by the total number of seconds available, that is this 19.2%. Okay, so we're using around 19% of all the available time for the computing that we need to do. As we do more, and when I began sending more messages per second, this started, being bigger. We're using more of our available time to do compute, actually executing cycles. One thing that I did not say explicitly, but I hope is part of your mental model for how the update graph processor works is this, right? Since we're defining that we're going to update tables every 1 second, when we don't have a lot to do and an update graph processor cycle starts at certain point in time, right? That may run for 50 milliseconds. What do we do the rest of the 1 second? We do nothing. We just let more rows show up to take all of them as a batch by the time we execute the next cycle, and then we run again. So there's some amount of idle time. So this kind of works similar to the concept that you see when you look at the top utility, right? We're talking about some amount of compute utilization and some amount of idle time. Again, the analogy is not perfect. The mapping is not one-to-one, but it's a useful way to think about it at a first cut for basic monitoring, I believe. Okay, cool. So I'm going to really restart now. I'm going to stop this. This is just my little script to stop Docker Compose and do a full cleanup. I do Docker Compose down, and then after doing down, I do Docker Compose stop, and then after doing stop, I do down. The reason I do Docker Compose down after doing stop is because I want a full reset of the transient data in the images, right? In the actual file system images, right? The reason I need that is because if I don't do down, if I only do stop, I have all the red panda context of all the messages that were already sent as part of the backend store for Kafka. I don't want that. I want a really clean slate, okay? Okay, so we don't have Deephaven running anymore. I'm going to start again, okay? We're starting again. Redefining the tables. Loading the script. Rearranging the tables. Now that the scripts are loading, going back to the one table that I care about, we have our ticking tables here, data is flowing, stuff is happening. Just 50,000, sorry, just 50 messages per second, very low load right now. Okay, we have our two tables of interest, the raw logger here, the view that we care about, more user-friendly on top. This is the one that I really want to show you, so I'm going to make that one have more space. And now I'm going to use my little script to do something a little bit more interesting. We're going to do 100,000. You probably cannot hear it, but the fan in my workstation is like spinning right now. 100,000 is interesting. The computer is making an effort. We probably need the next row to show up. So now we are at 62% of utilization, okay? So this is actually not that different from what we saw at 50,000 messages per second. We are not taking that much more effort in pushing this many rows, okay? The memory is going down. It's going down at a rate of like 400 megabytes every 15 seconds, if you look at this. So you can see that we will not be able to be running this way for very long, right? Eventually, we will run out of heap. The available memory is going down pretty quickly. So now I'm going to go to 150,000 messages per second. Have some GC happening right now. The GC is going to start pretty soon, by the way. As soon as the amount of garbage that has been accumulating exceeds the threshold. So this is not, you should not consider GC activity happening as a signal of a problem. It's not a problem, it's normal, right? At the beginning, when you don't have anything defined, of course, that's not happening, but an amount of around 5% of GC is normal. Okay, so now we see that we are having some other interesting things happen, okay? The number of update graph processor cycles on budget went dramatically down, and at some point we touched 15%, but now it's 0. And a second interesting thing is happening. The number of cycles that we can run is not around 15 anymore. It's actually going down. We see the number of cycles at this point, for instance, is 11. Next sample showed up, now is 10. They are taking more than 1 second, so we cannot run as many in a 15-second interval, okay? If we look at the max is going up. The median is also going up, which is important because if just the max was going, if you just have one sample of the max, that may be an outlier, might be one sample out of whack, something weird happened. Your computer was like, taken because there was some video that you were watching in YouTube. Who knows, right? In fact, there was an outlier here. You see the 2.5. That's an outlier on top of our high activity, right? And the time ratio, right? We are actually here very close to using all the available time in the 15 seconds for the update cycles. We don't have anything to spare. So now we are literally falling behind, right? We cannot run updates at the rate that we said we wanted. We cannot update tables once per second. Now, one interesting thing that I would say in terms of how Deephaven behaves, okay? We start updating less frequently, but we are still pushing data in a way where we are not falling behind in terms of actual Kafka messages. We're actually able to process our Kafka messages. If you look here, this table is part of the demo. It's not part of it has to do with the data that I'm sending to Deephaven. It doesn't have to do with the TableLoggers that I'm talking about. This table is part of the data of the tables that we define to track how we are doing in this particular demo. This is telling me that we have 2 seconds since the last message showed up in Kafka, right? So the last message that we managed to push through to update all these tables is like 2 seconds ago. So despite the fact, right, that we are running cycles that are taking longer, when we do run the cycle, we manage to keep up. Okay, so that's pretty much it. I'm going to stop this because otherwise you pretty soon are going to see that run out of heap black screen. And now I want to open it for questions if you guys have any.
Can you comment about how parallelization in Deephaven impacts or is related to what you've been talking about?
I think Ryan would be a lot better prepared to do that than me. Ryan, you want to comment on that? Crickets? I mean, maybe he's not here. So even Pete may know this better than me, honestly. Seriously. I know there is some work in Deephaven for some operations to actually do multi-threading in terms of selects for multiple columns and updates on multiple columns. I am actually not aware in detail of which operations support that. My understanding is that there is actually more support, or at least at some point in the past, there was much more support in Deephaven Enterprise than there actually is in the Deephaven community because it was not port over. I think Charles recently ported some of that, but again, I'm not aware of the details of what actually is parallel or not. Okay, now from the point of view of what we're showing in this table, which I think is what you are asking about in terms of what it means, right? Anything that is happening in parallel is still happening inside the budget that we have for the update graph processor, okay? So if one particular update graph processor cycle is running, any parallelization, any multi-threading that we manage to do is essentially happening inside that same interval. So I think these metrics are a little bit more complicated to think about when you have multiple threads involved, but not from a high level in detail, but not from a high level perspective from the point of view of this is the available time to do work. This is how much of that time you're actually using. By being able to use more thread, you can make more effective use of that time. You can do more in that time, right? Let's say that I have some kind of like, update operation that is updating multiple columns. And for each column definition, it can run in parallel because each column is one thread. Then you are going to be able to update more columns compared to a machine where that's not happening, a configuration of Deephaven that doesn't have that, a machine that has less CPU threads. Okay, but I will be with you in a second, Andy. But from the point of view of thinking about, I have a 15-second interval as my available time to work, and during that time I'm doing work for this period. I think it's still a useful metric of utilization. At that point, it's not really CPU utilization because there are multiple angles to what a CPU means in that context. Andy.
Yeah, so I mean, if you want, I could elaborate a little bit more about
Great.
what multi-threading we have and what it does. Now, I'm not as tied into the community, what's been ported over to community, but in terms of there are really two types of parallelization that we deal with. There are some operation parallelizations, which you mentioned. So we have some for where, and we have some for update. I'll talk about those separately. But the other one that we have is parallelization of the individual updates within the update graph processor. So, for example, if you have several tables within the DAG, and those tables are independent of each other, so they don't have any common parents or whatever. Then as those rows tick in from whatever sources are populating the roots, the updates themselves will be processed in parallel if you configure it that way. So that's one level of parallelization. Now, within some of the operations, there's actually one I forgot to mention, which is table map parallelization. But I don't think you have table maps yet. I don't remember. You do? Okay. So in where the engine, if you tell it to, will basically look at the columns that you have available, process the columns as much as it can in parallel, but it will also try to chunk them out into smaller batches and then process the batches in parallel themselves as much as it can. And then update will look at the dependencies between formulas within your columns, and it will try to process those individuals in parallel as much as it can, and it'll continue to spawn more threads based on, you know, whether previous dependencies have been completed and that sort of thing. And then the last one, and this isn't so much an automatic parallelization as it gives you the tools to parallelize with table maps. You can, so for example, by external, you take a table, you break it up into smaller tables based on keys. You can tell the engine to treat that table map as a table itself. And then when you perform operations on that table, so like you say, hey, do by external as table, and then you do aware or an update or something else. The fact that that table map has n tables in it means that you can, as the user, spread that work across all those tables in different threads if you want to. That's kind of more of a manual process, but it's there. So anyway, hopefully that gives
really amazing, though. It's a lot more than I imagined we had. It sounds really good.
Yeah, it's really neat. Charles did some really great work on the where and the update. It's pretty cool.
Any other questions, guys? Okay, so to close, right, reach out to those views that are more user-friendly. At a minimum, you're going to get to look at time in time-friendly units, like, you know, seconds with decimal places, instead of billions of nanoseconds, which are hard to look at. And when you actually need the detail, because you're probably coding something, you want to extract some piece of data from the raw data itself in the loggers, and you're doing like some Python for it, then use the loggers. But in general, if you're just browsing data to try to make sense of what's going on in an interactive console, please use the views. Do not use the raw data. That's it. Thank you, guys.
Thanks, Cristian.
Thanks.